Throughout the grand narrative of human history, one constant has defined our journey, marking the chapters of our ascent. It is not the empires we have built, nor the philosophies we have written, but the very materials we have learned to shape and master. These materials are the fundamental building blocks of civilization, the physical language through which we express our ingenuity, our ambition, and our desire to transcend our limits. Each new discovery, each innovation in material science, has unlocked a new paradigm of possibility, fundamentally altering how we live, work, and connect with one another. It began with the Stone Age. For nearly 3.5 million years, our ancestors learned to see the potential hidden within ordinary rock. By striking flint against flint, they sculpted the first tools: axes, blades, and spear points. This was not merely about creating sharp edges, it was the dawn of technology itself. These simple implements allowed us to hunt more effectively, build sturdier shelters, and ultimately to spread from the heart of Africa to every corner of the globe. The mastery of stone was the first great leap of human consciousness. Then came the Bronze Age, a revolutionary step forward born from the fires of the kiln. By discovering that melting and combining soft copper with tin could create a strong, durable alloy, we entered the age of metallurgy. Bronze gave us superior tools for agriculture, magnificent objects of art, and formidable weapons that redrew the maps of power. This new material demanded complex trade networks to source its rare ingredients, forging the first truly interconnected global economies and giving rise to sprawling, powerful civilizations. The Iron Age followed, democratizing metal. Iron, far more abundant than copper or tin, put powerful tools into the hands of the many, not just the few. It allowed for the creation of the iron plow, which dramatically increased food production and supported booming populations. It armed the great empires of the classical world, building roads, aqueducts, and cities that stood for 1,000 years. Iron was the backbone of the ancient world, a symbol of strength and endurance. In the 20th century, our focus shifted from the macro to the micro. We entered the age of silicon. By purifying a common element from sand and mastering its unique semiconductor properties, we invented the transistor and then the integrated circuit. We learned to etch impossibly complex worlds onto a tiny chip, giving birth to the digital revolution. From massive mainframe computers to the smartphone in your pocket, our entire modern existence, our communication, our economy, our very knowledge, is built upon this foundation of meticulously engineered silicon. Now, as we navigate the complexities of the 21st century, we stand on the cusp of another profound transition. A new material age, defined by a substance so revolutionary, so counterintuitive, it seems to have emerged from the pages of science fiction. It challenges our understanding of what is possible, appearing to defy the conventional laws of physics that govern the world we know. Imagine a material 1,000,000 times thinner than a single human hair, yet stronger than diamond and over 200 times stronger than steel. A material so light that a sheet large enough to cover a football field would weigh less than a single gram. A material that conducts electricity with virtually zero resistance, far more efficiently than copper or any other metal on Earth, and conducts heat better than any other known substance. This is not a theoretical concept. This material exists. It is a one-atom thick, perfectly flat sheet of pure carbon atoms, arranged in a hexagonal honeycomb lattice, and it is poised to change everything. Welcome to Eco-Innovatech. Today we are exploring the world's first two-dimensional supermaterial, graphene. This is the incredible story of a Nobel Prize-winning discovery, one that didn't require a billion-dollar particle accelerator or a massive research facility. Instead, it was born from curiosity, ingenuity, and a tool you can find in any office drawer. It was made with nothing more than a piece of graphite, the same material found in a pencil, and some ordinary sticky tape, unlocking a material with properties so extraordinary they border on magical. In this series, we will explore how this miracle material is set to solve some of humanity's greatest challenges. we'll see how it can create a new generation of hyper-efficient, transparent solar panels that could turn any surface into a power source. We'll investigate its potential for unbreakable super batteries that charge in seconds, revolutionizing energy storage and electric vehicles. We will even journey to the heart of a star on Earth and discover how graphene could help us finally achieve the dream of limitless clean energy from nuclear fusion. Join us as we enter the graphene age. The story of graphene, a material poised to redefine our future, begins not in a gleaming, futuristic facility, but in a relatively ordinary lab at the University of Manchester in 2004. It's a story that reminds us that sometimes the most profound revolutions start with the simplest of tools and a spark of human curiosity. To understand graphene, we must first look at something far more common: graphite. For centuries, we've known it as the soft, gray solid that leaves a mark on paper, the very heart of a pencil. Scientists had long understood that this humble material is composed of countless layers of carbon atoms, stacked one on top of the other like an impossibly vast deck of cards. Within each layer, the atoms are arranged in a perfect hexagonal pattern, a beautiful and incredibly strong honeycomb lattice. Carbon is nature's master builder, capable of forming wildly different structures, or allotropes. The same atoms that form soft, opaque graphite can also arrange themselves into the crystal lattice of a diamond, the hardest natural substance known. The key is the arrangement. For decades, physicists and material scientists were captivated by a tantalizing question. What if you could isolate just one of those single atomic layers from within a piece of graphite? They theorized that such a two-dimensional material, a perfect, one-atom thick sheet of carbon, would possess properties that bordered on the magical. But this idea came with a significant hurdle. Prevailing scientific theory, based on the work of physicists Landau and Peierls in the 1930s, argued that perfect two-dimensional crystals were thermodynamically unstable. They should curl up, wrinkle, or simply disintegrate at any temperature above absolute zero. For decades, the consensus was clear. Isolating a single stable layer was not just difficult, it was considered impossible. The breakthrough, when it came, didn't emerge from a billion-dollar particle accelerator or a state-of-the-art fabrication plant. It came from a moment of playful curiosity born out of a unique lab culture. Professor André Geim encouraged his team to conduct Friday night experiments, unconventional, often whimsical explorations outside their main research projects, designed to foster creativity and serendipity. It was during one of these sessions that Geim and his colleague, Konstantin Novoselov, turned their attention to graphite. They weren't the first to try to obtain thin layers. Others had attempted complex, often destructive methods of grinding and polishing. Geim and Novoselov's approach was disarmingly simple. They used a standard piece of Scotch tape, pressing it onto a small chunk of graphite and peeling it away. As they lifted the tape, it took with it dozens of layers of graphite. They then took that same piece of tape, folded it over, and stuck it to itself, peeling it apart again. With each peel, the graphite sample was cleaved in half, becoming exponentially thinner. They repeated this simple mechanical exfoliation again and again. It was a low-tech, almost mundane process, yet it was achieving what decades of high-tech efforts had failed to do. The final crucial step was to transfer these ultra-thin flakes from the tape onto a substrate of silicon dioxide. Under a standard optical microscope, most of the flakes were still far too thick. But among the scattered carbon debris, Novoselov noticed something. There were flakes so impossibly thin that they were nearly invisible, detectable only by a subtle change in the color of the silicon wafer beneath them. They had found it. It was a single, perfect, two-dimensional crystal of carbon, the impossible material, made real. It was graphene. For this beautifully simple yet profound discovery, Andrei Geim and Konstantin Novoselov would be awarded the 2010 Nobel Prize in Physics, just 6 years after their initial publication. The award citation celebrated their groundbreaking experiments regarding the two-dimensional material graphene, an achievement that had opened the door to a whole new frontier of physics and material science. What they had unlocked was not just a new material, but a material of superlatives, a substance that seems to defy the normal trade-offs of the physical world. It is the thinnest material ever created, 1,000,000 times thinner than a human hair, yet it is over 200 times stronger than steel. A hypothetical sheet of graphene the thickness of plastic wrap could, in theory, support the weight of a full-grown elephant. It is virtually transparent, absorbing only 2.3% of visible light, making it appear almost invisible to the naked eye. Yet, despite this transparency, it is so dense that not even a helium atom, the smallest of all atoms, can pass through its tight atomic mesh. It is the ultimate barrier, and its electrical properties are perhaps the most astounding of all. It is the most conductive material ever discovered at room temperature. Electrons flow through its perfect lattice with almost zero resistance, moving as if they have no mass at all, at speeds approaching 1/100th the speed of light. This phenomenon, known as ballistic transport, is a physicist's dream. Furthermore, it is an exceptional thermal conductor, better than diamond or copper, meaning it can dissipate heat with incredible efficiency. It is strong, light, flexible, transparent, and supremely conductive. No other material in existence combines this portfolio of extreme properties. Scientists, engineers, and innovators around the globe immediately realized that a material with such a unique and powerful combination of properties wasn't just a laboratory curiosity, it was a key. A key to unlocking a new technological era with the potential to solve some of humanity's most pressing challenges. The age of graphene had begun. In our global quest for a sustainable future, few technologies hold as much promise as solar power. Every hour, the sun bathes our planet in more energy than humanity consumes in an entire year. Capturing just a fraction of this power could solve our energy needs indefinitely. And it is here, in the heart of the renewable energy revolution, that graphene is poised to make one of its most profound impacts. One of its first and most promising applications is in fundamentally revolutionizing solar power. For decades, silicon has been the undisputed workhorse of the solar industry. Today's silicon-based solar panels are a mature, reliable technology. But they are also approaching a hard physical boundary, a ceiling on their performance known as the Shockley-Queisser limit. This theoretical maximum dictates that a single-junction silicon cell can never convert more than about 33% of the sunlight that hits it into electricity. In practice, commercial panels are even lower, typically in the 20 to 23% range. The reason for this limit is twofold. First, silicon is only efficient at converting a specific slice of the sun's spectrum. High-energy photons, like blue and ultraviolet light, have their excess energy wasted as heat, which can actually degrade the panel over time. Low-energy photons, in the infrared spectrum, simply pass right through without being absorbed. Second, the very design of the panel creates inefficiency. To collect the electricity generated, a grid of thin metal wires must be printed on the surface. These wires, though small, cast a shadow, blocking a portion of the light from ever reaching the active silicon layer. They can only convert a fraction of the sun's energy into electricity. Graphene changes the game. Let's first address the problem of those shadows. The current material used for transparent electrodes in high-efficiency cells is often indium tin oxide, or ITO. It's conductive and mostly transparent, but it's also brittle, expensive, and relies on indium, a rare and geographically concentrated element. Graphene offers a near-perfect replacement. Because it is both fantastically conductive and, at a single atom's thickness, more transparent than glass, it makes an ideal material for transparent electrodes. By replacing the traditional metal grid or the brittle ITO layer with a single continuous sheet of graphene, we eliminate the shadows entirely. This allows up to 4% more sunlight to reach the active photovoltaic material below. It's a simple, elegant solution that could instantly boost the efficiency of any existing solar cell technology it's applied to, without redesigning the entire cell. This alone would be a significant step forward. But the true revolution lies not in improving old designs, but in creating entirely new types of solar cells. Graphene is a key enabling material for next-generation photovoltaics, like flexible, lightweight perovskite solar cells. These cells are incredibly promising, but often degrade quickly when exposed to moisture. A thin, impermeable layer of graphene can act as a perfect barrier, protecting the delicate perovskite crystal and dramatically extending its operational lifetime from hours to years. This brings us to the most transformative property of all. Unlike silicon, which is picky about the light it absorbs, graphene's unique electronic properties allow it to absorb photons from across the entire light spectrum. From the highest energy ultraviolet through the visible colors and deep into the far infrared, the part of the spectrum we feel as heat. This is a paradigm shift. It means a graphene-based solar cell could be vastly more efficient than silicon, capturing energy that is currently lost. But more than that, it unlocks the ability to generate power in the dark. Through a phenomenon known as the thermoelectric effect, graphene can generate a current from a temperature difference. This means a panel could continue to generate power from ambient heat long after the sun has set, drawing it from the residual warmth of the ground and air. The potential is staggering, a solar panel that works 24 hours a day. While challenges in mass production and integration remain, the path is clear. From incremental boosts in today's panels to entirely new architectures that harvest the full spectrum of the sun's power and even the ambient heat of the night, graphene provides the blueprint. It is the path to a solar panel that wastes almost no energy, bringing us closer than ever to a world powered by clean, abundant, and limitless energy from the sun. The second great challenge of the clean energy transition is storage. Our modern world runs on lithium-ion batteries, but they are slow to charge, degrade over time, and have a limited capacity. Graphene is poised to shatter all of these limitations. By incorporating graphene into the electrodes of a battery, we can create a supercapacitor. Graphene's incredible surface area and conductivity allow the battery to charge and discharge at an astonishing rate. Imagine an electric car battery that could be fully recharged, not in 30 minutes, but in 30 seconds. Imagine a smartphone that charges in the blink of an eye. Furthermore, graphene makes batteries more durable. It creates a flexible, unbreakable framework for the electrodes, preventing them from cracking and degrading over thousands of charge cycles. A graphene-enhanced battery would not only charge faster, but it could last for the entire lifetime of the device it powers. This would dramatically reduce our demand for raw materials like lithium and cobalt, and create a world with far less electronic waste. As our world faces a growing water crisis, the ability to turn seawater into fresh water is becoming a critical survival technology. The current method, reverse osmosis, requires forcing water at immense pressure through a polymer membrane, an incredibly energy-intensive process. Graphene offers a far more elegant solution. A one-atom thick sheet of graphene is the ultimate molecular sieve. Scientists can now poke tiny, precisely sized nanopores into a graphene sheet. These pores are just large enough to allow a water molecule to pass through, but are too small for the larger salt molecules dissolved in the seawater. A graphene-based desalination filter would allow water to pass through with almost no friction, requiring a fraction of the energy of reverse osmosis. It would make it possible to build small, low-cost, and even portable desalination units that could provide clean drinking water for coastal and arid communities around the world. It is a simple physical solution to one of humanity's most complex resource challenges. Perhaps the most profound and futuristic application of graphene lies in helping us achieve the ultimate clean energy source: nuclear fusion. The greatest challenge in fusion energy is containing a plasma hotter than the core of the sun. The most promising method is a device called a tokamak, which uses the world's most powerful superconducting magnets to suspend the plasma in a magnetic cage. Graphene's incredible strength and thermal properties make it a super material for building the components of these fusion reactors. It can be used to create structural materials that can withstand the intense heat and neutron bombardment inside the reactor. As a superconductor, it could enable the creation of even more powerful magnets to contain the plasma more efficiently. Graphene is one of the key enabling materials that could help us finally crack the code of fusion and unlock a future of limitless, clean energy. The story of graphene is a powerful reminder that the next great technological revolution might not come from a new line of code or a clever algorithm, but from our ability to understand and engineer matter at its most fundamental level. From a simple flake of pencil lead, we've unlocked a material that promises to give us cheaper and more abundant clean energy. Batteries that last a lifetime, a solution to our water crisis, and even the power of the sun itself. The journey from a lab curiosity to a global industrial reality is long and challenging, but the potential is undeniable. We are at the dawn of the carbon age, not the carbon we burn for fuel, but the carbon we program to build our future. Graphene is the first letter in a new alphabet of materials that will allow us to engineer a world that is stronger, more efficient, and truly sustainable. What do you think is the most world-changing application for a super material like graphene? Let us know in the comments. For more on the innovations that are building our sustainable future, subscribe to Eco Innovatech. Thanks for watching. Welcome to Eco Innovatech. Today we are exploring the world's first two-dimensional supermaterial, graphene.